So we have another 50-minute talk by Ziad Ismaili Alaoui. I hope I said your name properly, visiting us from the University of Liverpool.
Test? Okay, great. Hello, everyone. I'm a PhD student from the University of Liverpool. That might be the first talk from a British university. And I'm going to talk about compressing preferential attachment graphs. And this is joint work with Namrata, a postdoc from the University of Liverpool, and Sebastian Wild. Okay, so I'm going to give a quick summary before the talk. What is the talk going to be about? So there's a probabilistic model that generates preferential attachment graphs, that generates n-vertex graphs. The Barabachi-Albert model. So there are multiple models, but we decided to go with that one because that is one that is well studied and understood. Each graph generated by this model has a certain probability P of arising. And essentially, we want to design a data structure that compresses a graph generated by this model using close to log n over, log 1 over p bits, right? So the idea is that the less probable a graph is, the more bits or space we use, and vice versa. And we want the data structure to allow for efficient navigational operations on the graph. So what that means is that we are going to use a little bit more space, but at the same time, the operations will be faster. So this is some sort of trade-off between space and time. Right. Okay, so what is the Barabachi-Albert model? How does that work? So we fix parameters m and n. So n is going to be the number of vertices in the graph, and m is going to be the number of edges, outgoing edges of each vertex. So that means that we are going to produce an m regular graph, directed graph. So we create a vertex v1, so one first vertex, and at each step t from 2 to n, we create one vertex vt, and then we direct m edges from vt to vt prime, where t prime is less than t. So for one vertex to each, so from the vertex, we direct m edges to vertices that were appearing before the vertex that we have just created. And the probability of dt prime to be selected as an out neighbor of vt is proportional to its degree right before vt was created. So what that means is that while I'm selecting the m targets for vt, each choice is independent, okay? So the fact that I'm selecting one specific vertex does not make that vertex more probable to be selected for the second target of vt. Okay, so here's a quick example with n vertices. So we have v1, v2. So we don't really have a choice here. We have to direct all the edges from v2 to v1. For v3, we have two choices. v1 has a probability of, so it has a degree of 3, and the total degree of the graph so far is 6. So it has a probability of 3 over 6, and likewise for v2. So suppose that v3 directs all the edges to v1, it really likes it. For v4, we also direct m edges from that vertex to its preceding vertices, and we do the same one for v5. So we can also derive the probability of this very specific graph to arise from this model. So up to those vertices, it was pretty much deterministic. I didn't really have any choice but to direct all the edges from v2 to v1. So the probability is 1 up to those two vertices. Here I have, so for v1, the probability was 3 over 6. Since I directed 3 edges, so I multiply the probability. So I take the cube of that probability. And likewise, I can derive the probability for the other vertices. And the total probability using the product rule is just 1 over 9,216. Okay. An interesting fact about this model is that we have a perfect one-to-one correspondence between an undirected graph generated by the VA model and its directed version. So as you noticed, the last vertex has a degree of m, okay? So that means that we can uniquely reconstruct its directed version. We just take a vertex that has mean degree in the graph. By degree, I mean the number of undirected edges incident to the vertex. So in this case, that would be this one. And we direct all the edges from that vertex to the other vertices. And likewise, we can do the same for this one because it has the mean degree in the graph. And we continue like this. Okay, so back to the data structure. So we are given a directed graph G generated by this specific model. And we want to design a data structure that compresses G whose space usage is asymptotically instance optimal. So instance optimal here means that it's asymptotically using log of 1 over p bits, where p is the probability of the graph being generated, and also offers efficient navigational operations. So what I mean is, so an efficient one operation could be deciding whether 2 vertices are adjacent, for example. And I essentially want to do this efficiently. Right? I don't want only to compress the graph. I also want to have some extra space so that I can perform operations more efficiently than without it. Okay, so one natural thing to do first would be probably to relate this measure to a property, a structural property of the graph. Before doing so, I'm going to quickly define what an agency string is. So if we are given G directed graph, an agency string A of G is simply a string of alphabet vertex, the vertex set of G, and resulting from the concatenation of all the neighborhoods of the vertices of G, right? And each neighborhood can be defined in some, can be constructed in some arbitrary order. So quickly for this graph, for example, it's a little bit boring, but one possible way to construct A would be to have V1, V1, V1. Suppose that this vertex has only points to itself for convenience. For this one, all the targets are V1. Likewise for this one. For this one, we have V2, V2, V3, right? Because these are the out neighbors of V4. And for V5, the out neighbors are V4 twice and V3, right? It could be any permutation, meaning that there could be multiple ways of writing A. It doesn't really matter. I'm also going to define the entropy in this context. So it's essentially the measure of the uniformity of the distribution of the characters in the string. In this case, it's not the relative entropy of a character. It's essentially it's here defined as the relative entropy of a character times the size of the string. Right? And one nice result is that given an n-vertex directed graph G generated by this very model with probability P, log 1 over P is actually equal to the entropy of A, the adjacency string of the graph, with some error margin. And, well, that's nice. Now we want to devise a data structure whose space usage falls within that range, okay? Okay, so we have an adjacency string A, which contains all the information we need to make some structural queries. And a data structure that compresses A in near optimal space and allows for efficient queries on the string A could be very useful. And it turns out that such a data structure exists, and these are wavelet trees. So what is a wavelet tree? So suppose that you have a string S of size n and alphabet size sigma. There's a data structure that uses the empirical entropy of S, the string, plus little of n bits, and supports a few operations in log sigma time, sigma being the size of the alphabet. So access returns the element at position I in the string. So this is a very simple operation. Rank alpha Si returns the number of indices of value alpha in S in the prefix of S up to position I. So how many times alpha appears in all the positions from 1 to I in S, okay? And select returns the index of the ith occurrence of character alpha in S, right? Okay, so A is of size n times m, and naturally we can compress A using this data structure in the empirical entropy of A plus n times m bits, right? Because this is the size of A. And we can also support all of those operations in big O of log n time, right? And because here sigma is n, right? The alphabet of A is essentially the vertex set of the graph. So that means that sigma is equal to n in this case. Okay, so here are a few examples of navigational operations. For example, suppose that we want to find the jth out neighbor of vertex I. It's a very boring operation. It's very simple. Suppose that we want to get the second out neighbor of vertex v4. We only have to jump to this position in the string and shift j times to the right, right? So we just compute the value at that position in the string. Okay. Sorry, it's actually meant to be A here, not S. Sorry about that. Okay, next query, compute the in degree of VI. The in degree of VI is essentially the number of times VI appears in the string A. Again, we can simply use a rank query on the string. It's essentially the number of times that VI occurs. So rank query on the entire string, and that also takes log n time. And another one, find the jth out in neighbor of vertex I, assuming that such a vertex exists. So one way to do this, for example, suppose that we want to find the second in neighbor of vertex 3, right? Suppose that the second one would be, well, the second one would be v5, for example. So we only have to look for the second occurrence of v3 in A, right? We take the position, and the position will inform us about which vertex is a target of, is a source of that, of the vertex vi, okay? So we find the position x in A, where the jth occurrence of vi is, and the answer is simply the ceiling of that division. So the first part involves a select query to find the jth occurrence of vi, which takes big O of log n time, and this is a constant time operation. Okay, so to conclude, we have seen how to compress preferential attachment graphs generated by the BA model in space asymptotically instance optimal by supporting navigational operations efficiently. The scheme can be also extended to general graphs using an additional bit string. Unfortunately, in the interest of time, I can't really stress much on this, but I will be happy to talk about this later. A slightly better compression scheme can be achieved if you don't care about the labels. If you are okay with relabeling the vertices, you can even improve. Improve space by a little bit, and that's it. Thanks.
Thank you, speaker.